So today we'll be learning completely about NumPy. By the end of this video, you'll have mastered everything you need to know about NumPy for machine learning and deep learning. We're going to cover this from the ground up, and after watching this, NumPy will never be a blocker for you again. So NumPy stands for numerical Python, and it is a fundamental package for scientific computing. Now, every single machine learning and deep learning library you will use, whether it is TensorFlow, PyTorch, Scikit-learn, or Pandas, everything is built on top of NumPy itself. Okay, so understanding NumPy is not optional, it's just essential. Now, I'm just assuming you know stuff like basic Python or variables or loops, functions, etc. So, assuming that you guys know that, we'll jump right into the code. Okay, before we jump into code, I'll show you why NumPy is too important. So let's do a quick comparison. First, we'll see how we do it in the traditional Python way. What I've done is I've created a very large list in Python and then multiplied each element in that with 2. And then I'm trying to calculate the number of seconds it took. Now, as you can see, this is the time it took for a Python list. Now let's do the same thing with NumPy. Now, as you can see, it is much better when you're trying to do it with NumPy. Usually NumPy is like 10 to 100 times faster, and this happens because NumPy arrays are stored in contiguous blocks of memory and operations are implemented in C code. So look at how much cleaner NumPy code is also. You can just write NumPy array into 2 and do the same thing instead of writing a list comprehension like this. So this speed difference might not matter for small values like this, but in large machine learning datasets where you'll be dealing with millions and billions of data points, NumPy makes that feasible. All right, so let's start building our NumPy knowledge from scratch. Now, the core of NumPy is an ND array, which stands for n-dimensional array. And let's explore different ways in which we can create this array. So I have a variable. Let's create a variable called ar1d. And if you do np.array of and then give it a list, okay, then you would have created your first NumPy array. Now, if you take a look at the type of this array, you can see that it says numpy.nd array. And if I do arr1d.d type, you will be able to see that it notices automatically that all the values are called integers. Now, NumPy uses this d type attribute to store the data type, and this is crucial for memory efficiency. So this is how you could have created 1D array. Let's see how you can do a 2D array. You just pass in a 2D list instead of a 1D list. So as you can see here, we've taken a 2D list inside this np.array, and it's the same as the one which we have done previously. You can now see the 2D array which we have written, the shape and the dimensions. Now the shape tells us the dimensions. That means we had 3 rows and 3 columns in this case, and the end dim here tell us that we have 2 dimensions. Okay, that this array is 2 dimensional. Let's try creating a 3D array as well. Here we go. Now you can see the 3D array which we have created, and you can see the shape as well. The shape is 2, 2, and 2. Okay, so 3D arrays were very common in deep learning. Well, if you take an example of an image, it is usually represented as height, width, and channels. So where channels might be RGB. Now let's take a look at some automatic built-in array creation functions. If you want to create an array of some dimension with all zeros, you have a method called np.zeros. And in here you can pass the dimensions. That means 3 comma 4. That is 3 rows and 4 columns. And if I just run this, you can see that I have an array of 3 rows and 4 columns. But if I want to create an array consisting of all ones, NumPy also has a method for that, np.ones. And here you can just pass in the dimension. This time we'll create a 3D array containing 2 blocks, 3 rows, and 4 columns. And here you go. Now, if you want to create an array containing all of a particular value, you can create array by using this method called np.full. You'll give it a dimension, let's say 3 comma 3, and I can give it the value which I want to fill as well. Let's say 5. Now it will create a 3 by 3 array for you, 3 by 3 NumPy array with 5 filled in it. Finally, we can see that if you use the function np.I and then give it any values, it will create a 4 by 4 identity matrix. What is an identity matrix? The identity matrix is an matrix in which all of the values are 0 except the diagonals, which will be 1. If you put 5 here, it will create a 5 by 5 matrix having all the diagonal elements as 1. Now, these initialization functions are very useful in neural networks and stuff, often we use these to initialize weight matrices with zeros or ones or random values. Now let's take a look at a few other functions. Let's say you want to create a NumPy array consisting of all the elements from 0 to 9 or 0 to 10. In that case, you can use a function called np.arange. Arange, and in here you can put in the values 0 to 11, and once you run this, you'll get all the values from 0 to 10 with this 11 excluded. Okay, if you want to have a step of let's say 3 for each element, you can just specify 3 here on the side and you can get 0, 3, 6, 9. It's the same as running loops in Python. If you want to have linearly spaced values as well, you can use np.linspace. You can specify the values and the number of divisions you want to divide it into. So it will give you 5 values here between 0 and 1. This is super useful for plotting data. If you have any data which you want to plot, this might be very helpful for you. Okay, let's see how you can create some random arrays in NumPy. So what you can do is you can use np.random.random and then give it a dimension inside. This will create a random 3 by 3 array which has random values from 0 to 1. But what if you want values which are between, let's say, 0 to 100 of the size 3 comma 3? In that case, you can use np.random.randint, and here you can specify the start value, the end value, and the size 3 comma 3. Now you can see that you got random values from 0 to 100 with the size 3 comma 3. Every time you run this, you will be initialized a different random value. Now in ML, you might have heard about normal distribution, right? So in NumPy, you can create an array having normal distribution using a function called np.random.randn, and you can specify the size in it, and it will create you random from normal distribution. Now, finally, if you want to reproduce this random value somehow, you can set the seed using np.random.seed and then give it a random seed value. And every time you do a random value after this, every time you do a random value after this, it will always be the same. So this random initialization is very important in machine learning, where we initialize the neural network weights and we typically transform these random values from we typically use these random values from normal distribution. And the seed will ensure this reproducibility. So you'll get the same random numbers every time. Now let's see how we can create some arrays with using different data types. So we've seen we can use np.array and you can specify a list in there to create a NumPy array of integers. Okay, so let's just store this in a value x equals to, and then when I do x dot d type, you'll be able to see that it is an integer by default. But what if I want to create a floating point? I can just specify the values here like this. And then when I see that, hey, this is 1 point, so it is going to be a floating point. You can either specify integers inside here as well, and it will automatically be converted into float, all of them. The main concept behind a NumPy array is that all the elements in the array should be of the same type. If you have a string in the middle, this will not convert it into a float. This will be considered as something else. Now, there might be a question for you guys how you can convert one type of an array into another. All you should do is just type x dot as type and then give the value. So I want to convert it into float. So np dot float 64. And as you can see, I got the values as float. But if I give them as integers here, let's say, and do this, I'll get them as float. Now, let's say you have an array consisting of values 1, 0, 1. Now, if you convert this to boolean, you can see that 1 is being converted into true, 0 is being converted into false. Now, these data types matter a lot for memory efficiency because float 64 typically uses 8 bytes per element, float 32 uses 4 bytes per element, and in deep learning with millions of parameters, this will quite easily add up. Now, let's create another array. ARR is equals to np dot random dot randint. I create a random integer array between 0 to 100, and the size, let's say it's 4 blocks, 5 rows, and 3 columns. You can see it's created. You can view different properties and attributes for this array. So let's see what those are. If you do arr.shape, you will get a tuple consisting of the shape of the array, which is 4 rows, 4 blocks, 5 rows and 3 columns. And if you do arr dot size, you will be able to see the total number of elements in the array. And if you do arr dot ndim, you will be able to see the number of dimensions. Since this is a three-dimensional array which we have created, the return value will be 3. And if you do arr dot dtype, you will be able to see the data type of the array inside. And if you do arr dot item size, you will be able to see the size in bytes of each element. Okay, since this is int 64 which we are using, it is taking 8 bytes. If you do arr dot n bytes, you will be able to see the total number of bytes consumed to have this array. So these attributes are essential for like debugging when you are building neural networks or when you are building machine learning models. The shapes don't add up or something. These attributes will, save you a lot of time to understand where it is going wrong. Okay, now that we have the basic things out of the way, we'll talk about indexing in NumPy. Now, this is a very crucial, critical concept because indexing and slicing are how you'll access and manipulate your data, and you'll be using them continuously in your machine learning and deep learning parts. So let's just create a sample array. We'll call it ARR and give the value 10, 20, 30, 40, and 50. Okay, so in order to just access an array element, you can just do as a normal list. You can just use the square brackets and put the index of the element. So zeroth index is 10 in this case, so I got 10. The same works for negative indexing as well. If you do -1 here, you'll get the last element. And yeah, so on, you will be able to get a basic indexing values. But now let's look at slicing. So what you can do is you can specify in this array, in this square brackets itself, you can specify the start value, you can specify the stop value as well as the step. Okay, so if you do this, you'll be able to get certain values out of it. So let's say I was able to do 1 colon 4. In this case, you'll get the values from the index 1, which is 20, all the way till 4, but not the fourth index, which will be 20, 30, and 40. This is the fourth index, will not be taking the fourth index. Okay, and you can ignore the first parameter as well. If you ignore the first parameter, it will take from the beginning. It will automatically initialize this to 0. So this will give us the first three elements. Now, if you do the same with the last element, if you ignore everything from, if you ignore the last part, you will get everything from the index 2 till the end. Now you can use a step value here as well. By just doing 2 colons and then 2, it will give you every second element. And you can do the reverse thing as well. If you have -1 in here, it will reverse the whole NumPy array. If you do, let's say 1 to 4, with step 2, it'll give you each other value from these 1 to 4. So all of these are classic tricks which work in Python as well. And these happen to have the same usage in NumPy as well. Let's take a look at how you can do 2D indexing. I'll create a 2D NumPy array like this. And now we'll try to access this first element. Here you have two ways in which you can access. So you can just do this and then you will be able to get the value properly. Or you have another way where you can use a single square bracket and then specify them with commas inside. This also works. Okay. You can do the same thing. So 0th element, which is 1, 1 comma 2, which will give you 7 as the answer, which is this one. And -1 comma -1, you can use negative indexing as well. So that will give you the last element, which is 12. So in this case, in this way, you can use indexing in arrays. But what about slicing? So in slicing, you can divide this whole parts into two ways. So here, as you can see in 1D indexing, this one specifies the rows and this one specifies the columns. So in the same way, you can use this thing to make slicing as well. So you can specify the slicing in rows over here, over on the left, and slicing in columns over on the right. Let's take an example. So if I want to take 0th row out of all and get all the columns of the first row, I'll be able to do this. In this case, I got all of these values. I'm taking just the 0th row and all the columns in there. Okay. And 0th row, all the columns till the index 2, I'll be able to do that also. Now, if you want to get all the columns except the last one, you will be able to do -1. So that would be 1 comma 2 comma 3. and you will ignore the last index here. Or let's say if you want to get the first two rows and all the columns. Let's say you want to get the first two rows and all the columns. All you need to do is put put a colon and then type in 2. This will give you the values 0 to 1 in rows. And since you want all the columns, you will just put colon here. This will give you the first two rows in all the columns. Or let's say you want to access a submatrix which contains the first two rows and only 1 and 2 columns. Okay, so I want 2, 3, 6, 7 as the output. In that case, what I can do is I can just take array 2D of since it's the first two rows, it's the same as previous. Colon 2, which means from 0 to 1, you want the rows, and it will be 2, 3, 6, 7. Now, Boolean indexing is something which is very powerful in NumPy. It is very useful in machine learning also, where you can use to, filter out outliers, or you can select specific data points. You can use them based on condition. Tell you how you can use Boolean indexing. Let's say you have an array like so. And you can create something called as a mask. Now, what is a mask? Mask is something you will wear on top of your face, right? In the same way, a mask is something which you can put on top of an array in order to get the appropriate values out of it. So if I was able to do, let's say true, false, false, true, 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 and fill it up. Now, if I was to have a mask value like this, where each of them is a Boolean value containing either true or false, and if I were to apply this mask value to the ARR in like this way, you can notice that wherever there is a true value, whatever index there is a true value, you will be able to see that as the output. So in this case, the zeroth index, the third index, the fourth index, the fifth index, and the ninth index with true values in them, and the corresponding elements will be returned to me out. Now, there's different ways in which you can create this mask values. Instead of specifying this, I can create a condition for the array as well. So I can just write ARR greater than 5. Okay, so if I were to print this mask, you can see whatever elements are greater than 5 will have the value true in them. Whatever elements are less than 5 will have the value false in them. And now I can easily apply this mask to my array in order to get the values out. Now we can do the same thing for printing all the even numbers in it. So I can just take the mask as ARR modulo 2 is equals to 0. Now I can just say that ARR of mask will give me all the integer values in there. Instead of writing this in two lines, you can just take this and paste it over here. That will also do the same thing. Now, there is another way in which you can perform indexing as well. So that is called fancy indexing in NumPy. Now, what this essentially does is, if you have an array, let's say ARR is equals to np.arange 10 to 50 with a step 10. And if I print this out, I'll be able to say 10, 20, 30, 40. Now, let's take this as 60, 10, 20, 30, 40, 50. Now, let's say you have an other array called indices as np.array of 0, comma 2, comma 4. Now, if you print out the indices, this is how it would look like. And what you can do is you can use this indices array as index for array as well. So if you do ARR of indices, you'll be able to see the values which we have in our indices. So in this case, the zeroth index is 10, we got that. The second index is 30, we got that. And the fourth index is 50, you'll get that as well. The same thing will work for 2D as well. You can see here we've created np.arange will create the values from 0 to 12, and np.reshape will reshape any one-dimensional array into whatever we want. Let's take an example. If you do np.arange 1 to 12, 0 to 12, you can see that we got the values from 0 to 11. Now, if you take this into an array A, and once you take A dot reshape, and you can give this any value 3 comma 4, and then you'll be able to see that it is molded it into a value 2D array. Okay, all you need to know is the product of the dimensions over here should be equal to the number of elements in the array above. In that case only this will happen. If you were to put something else, it will throw you an error. Now that you know that, this will create a 3 by 4 array with 0 to 12, and the number of rows and the number of columns, you can do this and you will be able to get the value. So the number of rows would be 0, 0, 2, and the number of columns would be 1, 3. So if I just print out this ARR2D and we can compare it, as you can see, the rows are 0, comma 2. So that means this zeroth row and second row, and the number of columns is 1 comma 3. That means in the zeroth row it will take the first one, which is 1. In the second row it will take the third element, which is 11. Now let's say you have a array called ARR, which is np.arange of 1 to 6. Okay, so this array, you have this array. Now let's say you want to copy this array into something. You can do some other let's say it's called variable, or let's say it's called view. And what you can do is you can just copy the value of ARR into this. Now look at what happens if I try to change an element in the view. Okay, so let's say view of 0 is equals to 999. I try to type view of 0 is equals to 999, and if I print view again, I'll be able to see that the zeroth index value has been changed to 999. Now, if you print the original array as well, you can see that it changed to 999 as well. This happens because when you're trying to do view is equals to ARR, you're not creating an entirely new array in view. What you're trying to do is this array, whatever has been there, it's already been created. And a variable named ARR is pointing towards this array. Now, if you create view is equals to ARR, you are basically saying that view also points to the same array which I have created. So if you update view and you can view at the array, it will do the same thing. Now you might ask me how you can create a copy of the array. All you should do is just type view is equals to ARR dot copy. Okay. Now if you take a look at view, you can see the values are this. I'll make a change to this. I'll make the first value as 0 again. And if I was to print view, you'll see that it's 0 here. And if I print the array, you can see it did not change the value of array. So that is how you can, copy. Now let's take a look at the array operations. So we'll talk about array operations. This is where NumPy is really useful, and these operations are vectorized, meaning they are applied element wise. So let's say I have two arrays, ARR1 and ARR2. So you can just do ARR1 plus ARR2 to add them element wise. So 11, 22, 33, 44. Or you can do ARR2 minus ARR1, so that you can do element wise subtraction. You can do element wise multiplication in this way. You can do element wise division as well. So this is the element wise division, and you can do power to the element as well. So let's say you want ARR1 whole to the raise 2, so you can automatically just do that as well by just using double star 2. Now, you can use this with scalars as well. So if you do ARR1 plus 10, it will automatically add 10 to every single value in ARR1, which is 1, 2, 3, 4. And if you want to multiply it by 2 or something, you can see that every element is being multiplied by 2. Now, notice how we can add a scalar to an array, add a scalar to this, add this to this. So this concept is called as broadcasting, and we'll talk more about it in a moment. But this is one of the NumPy's most important features. Now, in NumPy, there are some functions called universal functions. These functions or these values have a lot of trigonometric values in them, have trigonometric operations in them. So we'll take a look at that. Now, if you want to create the value of pi in NumPy, all you can do is just type np.pi and you'll be able to get the value of pi, which is 3.14. I'll create an array containing the values 0, pi by 2, pi. Okay, so I have an array containing 0, pi by 2 and pi. Now let's try to apply some of these universal functions. Okay, I can just do np.sign of ARR and I'll get the sign value of the array. Now if I do np.cos, you can do cosine value as well. You can do cosine value as well. Or if you do np.exp, and if you pass an array in them, you will be able to see e to the power 1, e to the power 2, e to the power 3 values. Okay, or if you do np.log of let's say you'll pass items like 1, or np.e, which will be the constant e, and np.e to the power 2, which will be e square. Now if you do this, you'll be able to see 0, 1, and 2. Now, since the values are this, you can say that this logarithm is a natural logarithm with base e. You can use np.sqrt to do the square root of all the elements in the array. If you have an array consisting of both positive and negative values, and if you are looking at trying to do the absolute value of them, you can just do np.abs and you'll get the absolute value of the array. Every negative integer will be converted into positive integer. Finally, with floating points, what you can do is you can have several floating points in a NumPy array. You can use np.round of round function, np.floor function, and np.ceil function to round them off to some value. Now, round will just round them off to the nearest value. Floor will give you the lower point, and ceil will give you the upper point. So, floor of 1.23 is 1, ceil of 1.23 is 2, floor of 4.56 is 4, ceil of 4.56 is 5. So round will just take a look at whatever is closer, either the floor or seat, and will convert it to that. Now let's take a look at some basic statistics functions which you can use in NumPy. So let's create an array, a 2D array. And if you want to find the sum of elements of this array, you can just write np.sum and pass in this array, and you'll get the sum all the elements in the array. If you want to do the mean of all the elements in the array, you can just do np.mean and send all the elements in the array. Now the mean of all the elements is 5. And if you want to do standard deviation, it is np.std of array, which will give you the standard deviation of all the elements. If you want to do the variance, you can just do np.var of arr. That would give you the variance of all the elements in the array. And you can do np.min of all the elements in the array, so that you'll get the minimum value, and np.max to get the maximum value. Now if you want to create, if you want to have this sum of elements at throughout one dimension, that means if you want to have the sum of elements of all the rows, okay, or sum of elements of all the columns, you can do that as well. All you should do is you can specify np.sum and pass on the array, specify a dimension called axis. Now axis can take values 0 to n minus 1, where n is the number of dimensions. So if I put axis 0, you'll be able to see that I have the values from column wise sum. That means I've added it 1, 4, 7. I've added them and got 12. 2, 5, 8. I've added them and got 15. And 3, 6, 9. I've added them and got 18. If you specify axis is equals to 1, you will get them row wise. So 1 plus 2 plus 3 is 6. 4 plus 5 plus 6 is 15. And 7 plus 8 plus 9 is 24. So that is what we got. So understanding these axes is crucial. Basically, axis is equals to 0 means operation along rows. You'll get the column results, and axis equals to 1 means operation along the columns. It will give you row wise results. So in 3D array, axis is equals to 2 means across the channels. Now in an array, if you want to find the minimum and maximum index of an array, so if I have the array here and you want to find the minimum value, minimum index and the maximum index of the array, all you can do is just type np.argmax and pass in the array, and you will get the index of the array, So 8 here specifies 0, 1, 2, 3, 4, 5, 6, 7, 8. Eighth index over here. That is the position of it in the flattened array. If you were to do this with the same one-dimensional array, you will get the values 5 and 1. Now, one more interesting thing which you can do with 2D arrays is you can find the index of maximum values throughout an axis. So I can specify np.argmax of arr, comma, if I want to specify the row-wise maximum values, I'll specify axis is equals to 1. In this case, I'll get that second value, second and second in the rows are the maximum indices. Okay. If I specify axis is equals to 0, I'll get them column wise. In this case, 7, 8 and 9. Now, previously we have seen how you could add scalar values and multiply scalar values to the array. So this is the concept of broadcasting in NumPy. Broadcasting is basically one of NumPy's superclass, but it can be confusing at first. It is the way NumPy will handle operations between arrays of different types. So let's take a look at the rules of broadcasting. Now, the first rule of broadcasting is that a scalar value can broadcast it into any shape. The scalar can be broadcast into any shape. So let's say you have a 2D array like this, 1, 2, 3 and 4, 5, 6. Now, if you add 10 to this, this 10 value will be broadcast into the shape of 2 by 3. Okay, so essentially the 10 will be converted into a NumPy array of 2 by 3, and each element will be added. This happens automatically. So as you can see, the 10 has been added here. Okay, so the value 10 has been stretched to match the shape of this ARR value. Now, two arrays with the shape n comma m and n comma 1 will also broadcast. So if you take the example of this, you have a 2 by 3 array, 1, 2, 3, 4, 5, 6, and you have a 2 by 1 array. So what happens is this 2 by 1 array will stretch to a 2 by 3 array. Now, how does NumPy compare this internally is, first it will check the first dimension. The first dimension is matching. Now it will check the second dimension. The second dimension is not matching. In the second case, it will try to check if any of the dimensions is 1. If the dimension is 1, then that means it can stretch this 1 into this dimension, 3. So now it will try to stretch this 1 into 3. And this would essentially become 2 comma 3. That means we are duplicating these rows on here. So what should happen is, the first row in ARR should be added with 10, and the second row should be all be added with 20. So let's try and see if that works. As you can see, the first row adds has been added with 10, and the second row has been added with 20. Now this column vector 10 comma 20 will be get broadcast across columns. So the first row gets plus 20, and the second row gets plus, first row gets plus 10, second row gets plus 20. Now in the same way, n comma 1 has been broadcast, 1 comma m can also be broadcasted. So let's take this example. Now you have an array of containing the shape 1 comma 3, but the same array which we have seen here, we'll copy this. The same array which we have seen here has the shape 2 comma 3. NumPy will now take a look at the dimensions of these both when we are trying to add. It will check the first dimension. The first dimension itself is not matching. Okay, since it's not matching, what will it do? It will check if either of these dimensions are 1. If yes, if either of these dimensions are 1, it will replace this 1 with the dimension it wants to stretch it with. So it will replace this 1 with a 2. And then now every value in the every row vector gets broadcast down to row. So each row will get plus 100, plus 200, plus 300. Let's take another complex example. Let's say you have two arrays like this. Now the shape of this is 1 comma 3. The shape of this is 2 comma 1. Now again, likewise, NumPy will first look at the dimensions of these both from left to right. It will check 1 and it will check 2. Now once it checked 1, it will see, hey, is this dimension matching with this dimension? No, it's not. Now, does either of this contain 1 in them? Yes, it will contain 1 in them. So replace that 1 with the other one. So it will replace this 1 with 2. Now it will go check the second dimension. In the second dimension, you can see 3 and you can see 1. Now you can see that are these dimensions matching? No, they are not matching. So does any of these contain 1? Yes, it will contain 1. Now you can replace this 1 with the other one, which is 3. Now at the end, if both shapes are equal, that means broadcasting of this will work. So if I do ARR1 plus ARR2, that should work. But let's take this example. Now in this case, ARR3 has a shape of two values in them, and ARR4 has a shape of 3 values in them. Now NumPy will first check these both dimensions, the first dimensions. Are these both dimensions same? No, they are not same. So now it will see if either of these are 1, equal to 1. No, neither of them are equal to 1. So what will NumPy do? It will throw an error saying that, hey, this cannot be broadcast together. These operands cannot be broadcast together. So broadcasting works when dimensions are compatible. Either they're equal or one of them is 1. Okay. So understanding this will save you a lot of shape mismatch errors in the future. Now let's see how you can perform flattening of a 2D array. Let's say you have a 2D array like this. You can have a function called arr2d dot flatten. This will return a 1D array which has been flattened, and you can do arr2d dot ravel as well, and this will also return a 2D array. The main difference between flatten and ravel is flatten will return a copy of the array, and ravel will not return a copy, it will return a view whenever it is possible. Now if you have the same array and you want to transpose this array, all you can do is just type the name of the array and do dot t. This will automatically transpose this array. So 1, 2, 3, 4, 5, 6 rows will be made as columns and columns will be made as rows. So it will flip the rows and columns, and it is mostly used in linear algebra, matrix operations, and etc. Now let's see how you can expand dimensions in NumPy. Let's say you have an array 1, comma 2, comma 3. Okay. Now what if I want to add a new dimension? Now if I do the shape of this, arr.shape, you can see that it has only three values in them. Now, if I want to add a dimension at the beginning, that means I want to add a dimension saying 1 comma 3 here instead of just 3. What you can do, you can just do the same as ARR of np dot new access and give all the values in there, the remaining ones. So now if you do the shape for this, you can see that it's 1 comma 3. You've added a new access value here and you're retaining everything else in the same way. You can do the same thing by using reshape as well. So you can just do arr dot reshape and you can give a new access 1 here, and minus 1 means anything works at the end. Anything after anything works at the end, whatever you want to do. And however you want to arrange the elements later on, it's your wish. But I want 1 in the first place. That is what you mean by here. And if you do dot shape of this, you can see you got 1 comma 3. You've added a new dimension. Now, if you want to add it at the end, all you got to do is just uh, do, instead of putting it in the beginning, put it at the end. So here you go. You can see you got 3 comma 1. Now let's see how you can stack different rows in NumPy. Let's say I have two arrays. ARR1 is 1, 2, 3. ARR2 is 4, 5, 6. Now if I want to stack them on top of each other, stack the rows on top of each other, what I can do is I can just type np dot vertical stack and pass in both of these arrays in a form of a list. Now you can see that 1, 2, 3 and 4, 5, 6 have been stacked on top of each other vertically. If I do the same thing and instead of v stack, if I type in h stack, all these, both of these will be stacked horizontally. That means after 1, 2, 3, 4, 5, 6 will be stacked. Now in the same way, let's see how you can split as well. So I've taken an array ARR which contains the value from 0 to 11 and it contains it in the shape of 3 comma 4. Now if I do ARR dot h split of this np.hsplit of this array and specify the value 2, what it will do is it will split this horizontally. Now basically in NumPy terms, horizontally means across the columns. So across axis is equals to 1. So that is why it has split across the axis is equals to 1, which is like this. And so this is axis is equals to 1, right? So it has split horizontally like this. Okay. Now, if you do the same thing for V split, it will split it across axis is equals to 0. But there is no way you can split this into two equal parts. So I'll specify 3 here. So in this case, what it will do, it will take vertical split. So that means 0, 4, 8. This is axis is equals to 0. So it will split vertically into three equal parts. Now let's take a look at some linear algebra operations. Let's say I have two arrays A and B as this. Now if I want to find the dot product of A and B, I can just do np dot dot and specify A comma B, and that will give me the dot product of them, which is 1 into 4 plus 2 into 5 plus 3 into 6. Or you can use another thing called as the at the rate operator. So if you just do A at the rate B, that will also give you the dot product between them. You can use the same at the rate to perform matrix multiplication as well. So if I have an array ARR1 and the second array as ARR2 is equal to np dot I, and I'll be passing it as 3. Now if I do ARR1 at the rate ARR2, I should matrix multiply them and I should get the value. Because multiplying a matrix with an identity matrix is equals to that particular matrix itself. Here is another matrix multiplication example. You have a 2 by 2 array, 2 by 2 matrix and a 2 by 2 matrix. And once you can do C is equals to A at the rate B, and you can do that and you'll get a matrix multiplication of A and B. But if you use just the multiplication operator, you'll get the values as 1 into 5, 2 into 6, 3 into 7, and 4 into 8. You should note one point, you should know that at the rate will do matrix multiplication, star will do element wise multiplication. Now let's say you have another matrix A is equals to 1, 2, 3, 4. We've already seen how you can calculate the transpose of this. So you can just do A dot T to get the transpose. But if you want to get the inverse of the matrix, all you can do is np dot, you can do np dot linalg dot inv of A. This will give you the inverse of A. So I'll store this in an array called A inverse. And now if I do A into A inverse, I should get an identity matrix. Now you can notice there is some 8 point some value. This is a very small value. You can get this as some floating point errors. There might be some floating point calculation errors. or some stuff which is happening in the background. This is essentially equal to 8.82 into 10 to the power minus 16, which is very, very, very close to 0. Now, if you want to find determinant as well, you can do np.linalg dot det, and you can specify the value of a, and you can see that the determinant of this is 4 minus 6, which is minus 2. Now if you want to find the eigenvalues and eigenvectors, you can just do np.linalg.eig, and you'll get the eigenvalues and the eigenvectors of this array. Now there's another way in which you can do boolean masking. Let's say you have an array like this, and if you do np.where and specify a condition inside the array, you will be able to get the indices of the array wherever that condition is true. And you can just, let's say, store this here, and you can just do ARR of indices, and you'll be able to get, you can just run them and you'll be able to get them easily. If you want to sort an array, you can take an array and you can do np.sort, and it'll automatically get sorted. But if you want to sort it in place, you can just use the dot sort method and it will get sorted in place. But if you want the indices that would sort the array, you can use indices is equals to np.arg sort of array. That will give you the indices of what would sort the array. Now, let's say you have an array containing a lot of duplicate values. You can use np.unique in the array, and you will be able to see all the unique numbers in the array. And if you put comma return counts is equals to 2, return counts is equals to true, what you'll be able to see is we'll get a tuple of arrays. The first one will contain the elements in the array. I'll just add another two here for easier understanding. The first one will contain the number. First one will contain the unique elements. Second one will contain the count of the unique elements. So the element 1 occurs one time, element 2 occurs three times, element 3 occurs three times, element 4 occurs four times. So if you want to create an array containing null values, you can do that. So I'll do np.array 1 comma 2 comma, and then you can add a null value by using np.nan, and 3, 4, or if you can do infinity value as well, so you can do np.inf to get infinite values in the array as well. So there will be nan and then there will be infinity. Now there is a function where you can check if there is any nan values. So if you do np, I'll just store this in a array, a is equals to, but if you do np dot is nan, and if you pass the value a, it will show you wherever the nan value is present. Now, in the same way, you can use np.isinf, and you can pass a, and it will show you wherever it is infinity. Isinf also has two other functions. You can use isinf or isposinf. That means it will show you wherever there is a positive infinity, or isneginf, where it will show you wherever there is a negative infinity. Since our array has no negative infinity, it will show you as false. All right, so we've covered a lot in this video. Let's quickly go recap and see what we have learned so far. So we've seen the time comparisons between NumPy and non-NumPy. We have seen how you can create different arrays, what all attributes you can access from the array. You've seen how you can create array with all zeros, all ones, or with a certain value. You'll see how you can create the identity array. You can see how you can identity matrix. You can see how you can create an array from a certain range. You can see how you can create random arrays as well. After that, we've seen different array attributes, dot shape, dot size, dot endim. And you've seen slicing after that. You've seen how you can slice different arrays. And after that, you've seen masking, Boolean masking. So what this would just give you a certain way to show a certain number. And after Boolean masking, we have seen reshaping or indexing of this. And finally, after that, we've seen shallow copy, deep copy, and values, addition, subtraction, multiplication, division. After that, we've seen universal functions, sine, cos, exponential, log, square root, etc. We've seen rounding. You've seen float values, floor values, seal values, and you've seen mean, median, variance, standard deviation, all these aggregate functions. And later on, you've seen the maximum value, minimum value, argument of maximum value, and you've seen broadcasting with three different rules. You've taken an example of one which works, one which doesn't work, and we've seen flatten ravel. We've seen how you can add new dimensions to a NumPy array. we've seen the V split head split, how you can split it vertically, horizontally, and V stack head stack, where how you can stack them horizontally and vertically. And you've seen matrix multiplication, element wise multiplication, dot products, and different matrix properties like transpose or inverse or determinant or something like that. And we've seen more Boolean indexing over here. We've seen how you can show it over here. And you've seen the number, how to find the unique elements. You can see how you can add non elements or null elements or infinite elements. So, and that. So you now have everything you need to work confidently with NumPy in machine learning and deep learning projects. The best way to solidify is to, practice this, keep practicing it, and try implementing these examples yourself and experiment with different operations, build your intuition, and etc. So yeah, that should pretty much do for this video. If you found this video helpful, make sure to do like and subscribe. Drop a comment if you have any questions or if you want to see more content like this. Remember, NumPy is tool, and like any tool, you'll get better with practice. So start using it in your projects, and before you know it, these operations will become natural. So yeah, thanks for watching. I'll see you all in another one.